We are Team 19086. We are the Visual Natural Language Processing of Medical Images for Enhanced Value. We're sponsored by Dr. Slepian from the Arizona Center of Accelerated Biomedical Innovation. My name is Drake Sitaraman.
My name is Steven Santinello.
My name is Andrew Fergalan.
My name is Zara Sadek.
My name is Frank Sardavine, and I'll be discussing the introduction to our software.
Proper histopathological analysis is critical for medical professionals to determine the presence of diseased tissues. The current standard for histopathology involves a medical professional to determine the presence of abnormal tissue or cells within a sample. This process requires specialized training, is time-consuming, and subject to human error. The senior design team's innovative solution is a computer application, Fractalize, that allows medical professionals to select a histological image and output an image separated by a grid that is characterized by color frequency. The concept of this application is derived from natural language processing, where sentences are deconstructed to enable computers to contextualize and understand language. Fractalize segments an image into uniform sections termed image voxels, similar to how a sentence is divided into words. Color information from each division is analyzed to generate a color frequency. The relation of the color frequency to each grid section provides context to the image, thereby allowing a program to classify types of images and their pathology.
Now let's see the software in action. First, I'll click Import Image. I'm going to import a mouse histology image. Based on information from biologists, this mouse has epithelial ovarian carcinoma, also known as ovarian cancer. I'm going to use our software to investigate whether this darker shade of purple is indicative of ovarian cancer and whether this light shade of purple is indicative of a healthy mouse cell. To do this, I'll divide the image into 3x4 in order to capture this dark area of interest. I'll then select color as the feature we want to analyze. The user can either choose specific colors for a more granular color comparison or general colors. General colors tend to be better for histology images, so I'll select general light pink and general dark purple. Finally, I will click Fractalize. Notice how the software divides the images into grids, or image voxels, and exactly picks out the portion of the image that I showed before. The software has also reduced the number of colors from several million to only a dozen or two using a color binning method. This makes the image more conducive to deep learning for the future. I can now click on the image voxel, and the GUI will show a detailed color analysis of light pink and dark purple. Notice the strong presence of dark purple, with 53.44% of the image containing dark purple in this image voxel. This seems to correspond with our prior knowledge of ovarian cancer in the image. If we compare this to data from the analysis of the non-diseased cell, we can see 19.68% of the pixels are dark purple in the healthy cell, which is far less than that for the cancerous cell. We can also see far more light pink with 56.45% of the pixels compared to the 16.36% in the diseased cell. This data potentially indicates that a higher presence of light pink indicates a healthier mouse cell, and a higher presence of dark purple indicates a cancerous mouse cell. This is not conclusive data as it is only from one sample. However, what it does show is that our software has great medical research potential to find indicators of other diseases in all kinds of cells. I am now going to label this cell as epithelial ovarian carcinoma. This would be akin to a medical professional physically circling a cell of interest using a pen and paper method and writing down what they believe that cell to be. Labeling the cell also allows a medical professional to train a future deep learning algorithm. A future deep learning software would implicitly detect a strong presence of dark purple, highlight that cell, and show the percent chance that this cell is an ovarian cancer cell. I can then click Save Voxel Data and select a folder for the deep learning training dataset. Looking at the JSON file which I saved using the program, this shows the exact information displayed from the software was saved to the computer. The image which I clicked is also saved. With the completion of this project, our software is now ready to train a deep learning algorithm.
The preprocessing system is designed with the purpose of simplifying color analysis. Characterizing color quantitatively can be a difficult process, since colors are subjective and difficult to define. One such tool that helps us define color is the Hue, Saturation, and Value Color Model, or HSV. It defines a color with 3 parameters, as shown on the cone. Using this system, there is a lot of flexibility in color definition. This, however, poses a problem. In this model, we can have infinitely many individual colors. With so many unique values, the chance that any one color repeats in an image is effectively 0, which is not helpful for analysis. The team has put together a color binning algorithm to reduce the number of colors that can be detected and compared. This is done by looking at the HSV value of each pixel in the image and mapping it to the nearest defined value chosen by us. The end result is a series of bins and a reduction in the total number of colors. Let's see this in action. This program starts by defining a set of benchmark colors that we want to have in an image. It loops through every pixel and changes it to the nearest benchmark color, resulting in an image that has far fewer colors, as will be shown here. By using a simple percent error model, it was determined that no image lost more than 18% of its visual information, which was below the margin of 25%, which was defined as too much loss to retain meaning. The image is now ready for color analysis. The final step in the pre-processing algorithm divides the image into the user-specified grid size and shape, with several examples shown here. The image is then sent for feature extraction.
Features are extracted by using a predefined color library, which calculates the percentage of those predefined colors which are selected in the GUI. In this example, we have a histology image where the only colors of interest are broadly dark purple and dark pink. Similarly to preprocessing, the color library is defined using the HSV color space. Because the preprocessing reduces the amount of colors in an image, we are able to better see clusters of stained cells. Once generated, the values from each image voxel returns to the user and then are displayed on the GUI as we see here.
Proper histopathological analysis is critical for medical professionals to determine the presence of diseased tissues. The concept of this application is derived from natural language processing, where sentences are deconstructed to enable computers to contextualize and understand the language. Fractal Eyes segments histology images into uniform sections termed image voxels, similar to exactly how a sentence is divided into words. The simplicity of our GUI will make it easy for physicians to upload histology images and identify relevant features within an image to be able to get an analysis of the image. Our goal was to capture the part of the image that is abnormal and analyze that part, which Drake showed us earlier, where the software divides the images into grids and exactly picks out the portion of the image that is abnormal. There has been no such technology so far, allowing a medical professional to automatically label portions of a medical image which we as a team created. Fractal Eyes is a truly powerful tool that is a huge step forward in research for medical imaging. Thank you.